In today's lecture, we are going to see a very important concept of a Riemannian space. And actually, we are talking about the concept of geodesics. In fact, when you study the general relativity, then you know the idea of tensor analysis is needed, and without the concrete knowledge of tensor analysis, you can't study general relativity. So, in this playlist, I have started to discuss the important tensors. Some have already been discussed earlier, and now we are going to see some more important tensors that will be needed for the study of general relativity. And in this regard, today we are going to see a very important concept of geodesics. Actually, in this lecture, we will learn about this geodesic, that is what is this geodesic, how its differential equation can be obtained. And after that, by taking some numerical problem, we will clarify our concept. I hope everyone you have a concrete knowledge of Euclidean three-dimensional space. And you know, if you are talking about the Euclidean space, that is the three-dimensional geometrical space, then if I will ask you a question that what will be the shortest path or the shortest distance between two fixed points in Euclidean space, definitely your answer will be that the shortest path between the 2 points in Euclidean space is simply a straight line. In fact, now when you talk about the Riemannian space in general relativity or in tensor analysis, you have to generalize this idea. The idea that the shortest path or the shortest distance between two fixed points in Euclidean space is a straight line. When this idea will be generalized in case of Riemannian space, then that very path is actually called geodesic. So the idea of this geodesic is actually seen in case of Riemannian space, not in Euclidean space. In fact, a straight line is the simplest geodesic you may say. So how this geodesic is defined, let us see first of all. For this, let us consider that these A and B are 2 points which are fixed in a space. In which space? In Riemannian space. Then the distance between 2 points A and B will be either maximum or minimum or stationary. When you say stationary, what does it mean? It means compared with the nearby paths, this distance will be same. Okay? Actually, the path of extremum distance, when you say extremum distance, that means you are talking about the distance which is either maximum or minimum or stationary. In Riemannian space is called geodesic. Okay? So if this AB is the geodesic, then the length of this path AB will be either maximum in comparison to the nearby path, or it will be minimum in comparison to the nearby path, or it may be equal in comparison to the nearby path. So how we can define this geodesic? So you can say that geodesic is defined as the path of extremum distance or extremum length between any 2 points in Riemannian space. Okay? And for this, you can see this figure. I have considered the 2 fixed points A and B, and these 2 points are actually assumed in Riemannian space. Okay? How this geodesic can be obtained? What will be the actually mathematical condition using which we can determine the geodesic. If you consider that this ds is an elementary length of this path AB, then you know this ds is called line element, okay? And when you will integrate this line element ds between the limits a and b, then you get the total path length AB. And according to the definition, this path AB will be a geodesic if the total length AB, which will be actually equal to integral of ds between a and b, that will be extremum. Then that path will be called a geodesic. So the condition using which we can determine the geodesic is written as integral a to b ds must be extremum. Okay? And you have definitely studied the calculus of variation in classical mechanics. If you have not a concrete knowledge of calculus of variation of classical mechanics, I will suggest you go through my videos on calculus of variation in the playlist Classical Mechanics of my YouTube channel. There you will find several videos on calculus of variation. And actually, while dealing with the calculus of variation, we study about a variational operator that is denoted by this symbol, a small delta. This is called delta variation operator. If integral of ds from a to b is extremum, then when you will apply this variational operator on this integral, then that must be equal to 0. Okay? So you can say that delta operated on integral a to b ds is equal to 0. This is the required condition using which one can find the geodesic. Okay? When you say that one can find the geodesic, it means our aim is to find the general differential equation of this geodesic. So now we are going to learn how we can determine the general equation of geodesic. Actually, equation of geodesic is in fact a differential equation. So now our prime aim is to learn all the steps for obtaining the general equation of a geodesic. Okay? And for this we will define this ds in Riemannian space. You know, in Riemannian space, this line element ds square is given by this relation g jk dxj dxk. You know, this g jk is the metric tensor. Okay? And this is the expression for the line element in Riemannian space. Okay? Now we consider that the path connecting the points A and B is given a very small arbitrary displacement, let us say delta xm. Okay? So if the path will be deformed by giving every intermediate point on RB by the amount delta xm, but keeping this A and B fixed, then this equation 2 in this condition will give a proper value. What will be that? It means, in other words, you can say, now we are going to operate the variational operator delta on this equation 2. Okay? So when the operator delta will be operated on this equation 2, what will be our result? You can see, when delta will be operated on ds square, this will be simply 2 times ds times delta of ds. Okay? Now in RHS you can see there are there are actually the product of 3 quantities. So we must follow the rule of the differentiation of product of functions. Okay, so when you will operate the operator delta on the first function gjk, then you have to keep the other two functions dxj and dxk at ease. Okay, so the first term will be delta operated on this metric tensor gjk times dxj times dxk. Okay, now gjk and dxk are taken at ease, and the operator delta is operated on dxj, and in the last term we keep gjk and dxj at ease, and the operator delta is operated on dxk. This is a simple rule of calculus, you know. Now you can see what will be the value of this delta operated on gjk. In accordance with the definition of this delta variation, you may write delta operated on gjk equal to this much. This is del gjk by del xm delta xm. Here you have seen that delta xm is the arbitrary infinite sample displacement given to each point between A and B. Okay, so instead of delta gjk, we have written this del gjk by del xm delta xm. This is just definition of this delta variation operator. Okay, and now let us see the second term. In fact, in this second term you can see the expression is gjk times dxk and delta operated on dxj. Okay, and in the last term is also at ease. Now we have to actually find the value of this delta ds. Okay, and for this we have to divide this result by 2 times of ds both sides. So let us divide this expression both sides by 2 times of ds. So see the LHS. When you will divide this 2 ds times delta operated on ds by this 2 ds will cancel out, and only delta operated on ds in LHS will remain. Here the RHS will be also simplified by taking under account this particular result. You know, the operator dds, mark it, operator dds and the operator delta are interchangeable. If you write delta operated on dxi by ds, what are you doing here? Here, first of all, we differentiate this xi with respect to s, and then we operate the delta variation operator. Okay, but if you will interchange these two operators, it means at the place of delta now we will write dds, and at the place of dds now we will write delta. The result remains same. So we simply say that the interchange of the operators dds and delta are permitted. Okay, so wherever it will be needed, we can write delta operated on dxi by ds instead of dds delta xi, and vice versa. Okay, so utilizing this result and also by dividing this 2 ds in RHS, what will be the expression in RHS? Now you can see. See this first term. Here we will divide by 2 times ds. So there will be 2 in denominator and ds will be also in denominator. But if we will write extra ds in denominator, then you have to multiply it by ds. Okay, so let us see. I have done those algebra here. 1 over 2 has been taken as a common factor, and here there will be dxj by ds times dxk by, this ds is extra, because I have told you that we have to divide by 2 ds, but here we have written 2 ds times ds. So you can see I have also taken this ds in this multiplicative in numerator. So result remains same. And this term is at each. Okay. Now in the second this second term you can see gjk times dxk by ds, and instead of this we will write this dds delta xj. Okay. So this has been written as gjk times dxk by ds dds delta xj. And this, in the similar manner, you can see this third term will be written as gjk times dxj by ds, and instead of this, utilizing this formula, we can write ddx delta xk times ds. Okay. So in this way we have obtained the value of delta operated on ds. Okay. Now this value of delta operated on ds which you have obtained in this equation 3, let us use this value in equation 1. Equation 1 which actually refers the condition utilizing which we will obtain the geodesic or the equation of geodesic. So after using that value of delta operated on ds, equation 1 becomes like this. This is 1 over 2 integral a to b, and you can see this first term is at each. Okay. This second term here is at each. You can see I have written actually third term before, and this is your second term. Okay. Only there will be integral from a to b. Okay. Now you know, in any tensor equation, the dummy indices may be freely changed. Okay. So if you will change the dummy indices in the last two terms, that is in this term and in this term, if we will change the dummy indices, then what will be our result? You can see the first term is unchanged. This has been written exactly same as it was before. But now in these two last terms, as I have told you, we are going to change the dummy indices. So you can see, instead of here k, we will now write m. So this will be gjk jm dxj by ds times dds delta xk, but k is now written m. Okay. So there will be dds operated on delta xm. And in the second term again you can see this j will be replaced by this dummy index j will be replaced by m. So this is gmk and dxk by ds, and again here instead of j we will write m. So this dds operated on delta xm has been taken as a common factor. Okay, and ds is at each. So this equals to 0. I think you have understand that after changing the dummy index j in the last two terms, our result is this. Okay. Now you can operate this integral on both of these terms. So this first term is at each, only this integral has been operated on it, you can see. And also now we are going to operate this integral on this second term. So let us see, this is at each and this integral has been operated on it. Now actually this second integral can be evaluated by following the method of integration by parts. Okay. Following the method of integration by parts, you may evaluate the value of this second integral. So let us try to evaluate this second integral using the method of integration by parts. So now this first integral is at each. I have written that first integral at each, you can see. and see the evaluation of the second integral. Here we will consider this bracketed function gjm del xj by ds plus gmk dxk by ds. We consider it as first function. This is your first function. Okay, and this d ds operated on delta xm, we take it as second function. Okay, this is taken as second function. Now apply the rule of integration by parts. According to this rule, we have to write the first function times integral of second function. Integral of second function. First function is this much, and what will be the integral of this d ds delta xm with respect to s? This will be simply delta xm. You can see this when you will take integral of this d ds delta xm ds. This ds will cancel out, and you know the integral of differential of any quantity is equal to that quantity, because this differential d is cancelled by this integral. So this integral will be simply equal to delta xm, and limits are a and b. Okay. When you say a and b, it means you are talking about the value. So you can see here, this is your first term, first function, and this is the integral of second function, and limits are a and b. When you say a, it means a refers the value of delta xm at a, and b refers value of delta xm at b. But you know, points a and b are fixed. Points a and b are fixed, and delta xm is the arbitrary infinite simul displacement provided to the points between a and b. Since a and b are fixed, so they will not get displaced. Okay, they will not get. This is just like a string fixed at 2 points. When you discuss the standing wave in a string which is fixed at 2 ends, then you know always at the fixed ends there are nodes, the points which are permanently at rest, never get displaced. Just like that, I have assumed that this A point and point B are actually fixed, and all other points between A and B have been given this infinite simul arbitrary displacement delta xm. So this delta xm is 0 for the point A and also for the point B. So when you will substitute the limit, this term will be 0, and when this will be 0, this first term will vanish. So this first term vanishes. Okay? This first term will vanish. And what is the second term in accordance with the rule of integration by parts? In second term we write minus sign, and then we take integral of differential of the first function. This is your first function, and I have operated this operator d ds on it. This is differential of this first function. Okay, and integral of the second function, you have seen that this delta xm is the integral of second function. Okay, but as I have told you that this delta xm over the limits a and b is 0, so this first term vanishes, and therefore the above equation will be 1 over 2. Now you can see this first term is at each, and now what will be this second term? You can see I have taken integral here, and so this will be minus d ds operated on this function times delta xm ds. Okay, but you know this delta xm is what? These are actually the infinite simul displacements suffered by each point between the fixed points a and b. But these displacements are completely arbitrary. So for all values of delta xm, this integral will be 0, or the result defined in this expression will be valid, will hold only when the integrand, that is the coefficient of delta xm in the integrand, will vanish, will be 0. Have you understand? Since delta xm is arbitrary, it will have any value. So the cause of this 0 is not this delta xm. For all values of delta xm, the result will be 0 only when the coefficient of delta xm in the integrand of this integral must be equal to 0. So let us see what is the coefficient of delta xm in the integrand. That is 1 over 2 dxj by ds times dxk by ds del gjk by del xm, okay, minus dds gjm dxj by ds plus gmk dxk by ds, and that will be equal to 0. Okay. So this result we have obtained. Now let us see. When we will simplify this second term, you can see the differential operator d ds is operated on this sum of the two terms, and each term is a product of two functions. So again we will follow the rule of differentiation of product of two functions and simplify this second term. So your first term is at it has been written exactly same. But now let us simplify the second term. When you will operate the operator d ds on the first term, you can see if this operator will be operated on this gjm, then dxj by ds will be taken at each. And when it will be taken operated on this second function dxj by ds, then gjm will be at each. So you can see this is 1 by 2 times dgjm by ds and times dxj by ds. This is at each. Now gjm is at each, and the operator dds is operated on dxj by ds, that will be d2xj by ds square. Okay. Similarly, when you will operate this operator d ds on this second term, which is a product of gmk and dxk by ds, what will be your result? This will be, since there is minus sign, so this will be minus 1 over 2 dgmk by ds times dxk by ds, and minus 1 over 2 gmk times d2xk by ds square, and that will be equal to 0. Now, to simplify this result, you have to see these two important results. You know, djm by ds, this is equal to del jm by del xk times dxk by ds. And similarly, dgmk by ds is equal to del gmk by del xj dj by ds. Now we will utilize these two results in equation number 4. So when you will use these two results in this equation 4, what will be our result? You can see. Again you can see this first term is at each. It is never disturbed. But in this second term there is dgjm by ds. But instead of dgjm by ds, now we will write this much. Okay. So after writing this, this term is 1 by 2 dxj by ds times dxk by ds times del jm by del xk. Okay. And again this third term is at each. Now this dgmk by ds, this is equal to this much. So let us replace this dgmk by ds by this expression, and then your this fourth term becomes 1 over 2 dxj by ds times dxk by ds times del gmk by del xj. And again this last term has been written at each. Okay, so this is your result. Now actually we will do some algebra further to cast this equation in a proper form. You can see, taking this term 1 over 2 dxj by ds dxk by ds as a common factor, we can write the remaining terms in this manner. Okay, and again associate this these two terms of the second order, then your result is like this. Okay, now in this equation again we are going to replace the dummy indices j and k by l. You know, the dummy indices may be freely replaced by any other index. So in the last two terms in this second bracket, you can see here, in these last two terms we will replace j and k by l. If you will replace j and k by l, what will be your result? You can see. So this first term is at each, this is at each, you can see this is at each. And in this second bracket, instead of j we will write l, instead of k we will again write l. So your result will be what? This will be minus 1 over 2 glm. Instead of j, now I am writing l, and d2xl by ds square. Instead of j, again l has been written. Here instead of k we will write l. So this is gml d2xl by ds square, and that will be equal to 0. Okay. But you know, the metric tensor glm is a symmetric tensor. So utilizing its symmetric property, you can say that glm is equal to gml. So instead of gml, now we will write glm. And so the sum of these two terms will be what? That will be 2glm times d2xl by ds square. That 2 and this 2 in denominator will cancel out, and therefore our equation becomes this much. This term is at each, plus, actually here I have taken the minus sign as a common factor. When you will take minus sign as a common factor, you can see the sign of the terms in LHS will be just reversed. So the positive term now becomes negative and negative term now becomes positive. So these two negative terms is now positive, you can see, and this positive term becomes negative. Okay, and this negative, last negative term also becomes positive. But since in RHS there is 0, so that will remain 0, because minus 0 is not meaningless, is meaningless, that is simply 0. Okay, so here actually to cast this equation in a proper form, minus has been taken as a common factor. Okay, now let us see. We will multiply this result by this factor gmp. Here MP are superscript. These are metric, contraband metric tensors. Okay. So when you will multiply that equation throughout by this gmp, what will be your result? You can see the first term has been multiplied by this gmp. The second term is also multiplied by this gmp. But you know, we have actually seen my lecture on the Christoffel 3 index symbol in the previous video, and you have learned that 1 over 2 times this much, here 1 over 2 times this expression inside this bracket, that is actually equal to the Christoffel symbol of first kind, and that will be denoted by gamma M comma Lk. Can you remember? Because you have studied already this Christoffel symbol in my previous video. Okay? And the remaining factors are same. And again, you know, this product of GLM and GMP, this product is actually equal to the Kronecker delta PL. Okay? So instead of the product of GLM times GMP, I have written here Kronecker delta PL. Okay? And times d2xl by ds square, and that is equal to 0. But you know that when P will be not equal to L, then this Kronecker delta will be 0 and this second term will vanish. But if P is equal to L, then this Kronecker delta is equal to 1, and then this second term will become what? This second term will be d2xp by ds square. Instead of now L, we will write P, because when L and P are equal, then this Kronecker delta is 1. And again, in my previous video, you have seen how the Christoffel symbol of first kind and second kind are related together. You have just seen in my previous video that the product of the first kind symbol of Christoffel symbol and this GMP, that is equal to the Christoffel symbol of the second kind gamma pjk. You have learned it in my previous video. So instead of the product of this GMP times gamma m comma Lk, where gamma m comma Lk is the Christoffel 3-index symbol of first kind, this product gives you the Christoffel symbol gamma superscript p subscript jk. This is actually the Christoffel symbol of second kind. Okay? So finally, we get a differential equation which is d2xp by ds square plus dxj by ds times dxk by ds times Christoffel symbol of second kind gamma pjk equal to 0. Actually, this differential equation has been obtained on the basis of the condition for extremum, and this very equation is known as the differential equation of the geodesic, or you can say this is the general equation of a geodesic. In fact, you know, if we will put if we will talk about the Minkowski space, then P will be equal to 1, 2, 3 and 4, and substituting P equal to 1, 2, 3 and 4, actually we will get the different form of geodesic. Okay? Now we will see a very remarkable fact. If you consider that the distance between any 2 points on a geodesic is 0, the distance between 2 points on a geodesic is 0, then such a geodesic is called null geodesic. Okay? And that null geodesic is characterized by this equation along with this differential equation. This differential equation is the general differential equation. It will describe any geodesic, even the null geodesic. So along with this equation, a null geodesic is characterized by utilizing the condition this much: gjk dxj by d lambda dxk by d lambda equal to 0. Okay? So I think you have clearly understand what is geodesic, how the equation of geodesic can be obtained. Okay? And now when you will actually study the concept of general relativity, then you will find the application of this geodesic. So application part will be discussed when I will start providing videos on proper general theory of general relativity. Okay, thank you very much.